Hello everyone, I hope you're doing well. In this video, we'll be solving problem 21 from chapter 5 of Introduction to Statistical Mechanics by Roger Bowley. This is a requested video. One of my subscribers requested me to upload that video. So here we are doing this problem, and even if you, the one watching it, if you have any problems that you find it difficult to solve, then you can seek my help. I'm always here to help you all, and that's the purpose of this channel. Okay, so let's see the problem statement and we'll dive directly into the solution. The solution to other problems, ton of problems from the similar chapter and from other chapters, is already uploaded, and they are included in the statistical mechanics playlist. Okay, if you find it difficult to find the one you are looking for, then comment, I'll guide you. Let's see what statement says. By putting beta equals 1 over kBT, write z equals summation I e to the power minus beta ei. So they have rewritten the partition function here by assuming that 1 over kBT is equals to beta. Okay, that's simple. And show that this relation is true. Okay, we have to prove that relation considering this z. All right, then what we have to do, consider the second derivative of natural log of z with respect to beta. Show that we have to find out the second derivative of natural log of z with respect to beta, and we have to show that this relation satisfies. Okay, we have to prove that relation. And then what we have to do, the third thing that we have to do, is to prove that standard deviation in energy is given by this relation. Okay, and after proving the third thing, what we have to do, the fourth thing here, show that the average internal energy of a harmonic oscillator is this. That's the fourth thing to do in this problem. And the fifth thing is to calculate the average energy and the standard deviation in energy for a two-level system with energies E and negative E. So a total of 5 different things that we have to do here in this problem. So it would be a lengthy problem, maybe, or might be not, depending upon the length of the steps required to get the needed form. So let's quickly get started because it's a lengthy one. Okay, we'll start with z. Okay, we know that the partition function is given by partition function is given by, we'll start with partition function, which is represented by z sign. Okay, and that is given by, let's write it as original formula, which is summation over I e to the power negative ei by kBT. Okay, so this is the general formula of partition function, and let as given beta equals 1 over kBT, which implies that ei by kBT would be simply equals to beta ei. Okay, because 1 over kBT is beta, so we'll put 1 over kBT as equals to beta, and ei remains like that. So we'll replace this whole term in the power with beta ei. So the partition function becomes, so 1 becomes, since it's equation number 1, partition function becomes this. Okay, you should realize these steps. That's why I rewrote them, because it's needed, and you need to identify that that's the case, and that's the general one, and that's the one that we got after putting beta. So this is the partition function that will accompany throughout the calculations. All right, so here we can see the first thing that we have to prove. There are a total of 5 different things that we need to do in this problem. And the first thing in line is this relation. So we'll be solving it first. We'll proving it first, and then step by step we'll do all of the ones. So let me write it on paper, and we'll solve the left hand side and we'll make it equals to the right hand side. That's how we'll be doing it. Okay. We need to prove, you can write 1 here to show that it's the first relation that we are gonna prove. It's partial by partial beta of natural log of z, we have to prove that it is equals to summation I pi, that's the probability, ei, and that is equals to the average energy. Okay, this is the relation that we have to prove, the first relation that we need to prove. Let us call it as A. Okay, so what I'm gonna do is to simplify this side into this. Okay, we'll prove that this side is equals to this side, and since we have z, we can easily calculate this side. So we know that z is given by 2 here. So partial by partial beta of natural log of z would be equals to, this is left hand side, that is equals to partial by partial beta of natural log of z. What is z? Z is simply this. Okay, we write it simply like that. This is the whole term inside the natural log. Okay, and you cannot put natural log inside, it will remain outside. Okay, then now let's apply the partial derivative on this term, and let me tell you people that what is the derivative of natural log. If you are gonna find partial by partial x of natural log of let's say we have here y, let's say it's y here, so that would be equals to derivative of natural log of some term is equals to 1 over this term, reciprocal of that term, dot derivative of that term with respect to x. Okay, what you do is take the reciprocal of this term that is inside the natural log, dot take the derivative of this inside term with respect to this thing. Okay, so that's how we are gonna do here as well. So we'll have 1 over reciprocal of this term, that is like that, 1 over the thing that is inside the natural log, which is this whole term, I wrote it like that, dot partial derivative with respect to beta of this inner term as well. I'll call it as inner term. Okay, so 1 over inner term and derivative of inner term, that's how the derivative of logarithms work. Then we need to simplify it now. This term remains like that, it will not be simplified, but here the partial by partial beta will be applied on inside summation because beta is inside here. Okay, and what is the derivative of exponential terms? In order to find out the derivative of exponential terms, what happens is that the exponential terms comes as it is, dot the derivative of its power. What is power? It's ax. Okay, so exponential term remains like that, dot the derivative of its power. That's how the derivatives of exponentials with base e works. So we'll write the similar way here. Let us write it here, that is equals to 1 over summation ei beta ei dot exponential term as it is, e to the power minus beta ei dot derivative of exponent or power, which is minus beta, is minus beta ei, minus as well because minus is also in the power, and summation e to the power minus beta ei, and minus ei will come outside of the integral, come outside of the this derivative because it doesn't contain beta, only beta terms will be it will remain inside. So partial beta by partial beta, it's 1. So we are left with then we have this summation, and negative sign could be written here. It's ei e to the power minus beta ei. Okay, and we can write them like that: negative summation ei e to the power minus beta ei divided by summation I e to the power minus beta ei. Okay, and this is partial by partial beta of natural log of z so far. Okay, now since what is probability equals to, what is the formula of probability? That is equals to e to the power ei beta, in terms of beta, ei beta divided by z. Okay, this is the formula for probability pi. So we can see in the denominator this is equals to z, so we can replace it here. I wrote it here as a guide to see what necessary steps should be done. Okay, that is this term in the denominator was z. Okay, so I wrote it like that, and if you see that here e to the power minus beta ei divided by z, this is pi, so we can replace this term here with pi, negative ei pi. Okay, this is partial by partial beta natural log of z. Next, we can actually take this negative sign into this side. Okay, so instead of writing here, we can write it here as well, minus partial by partial beta natural log of z, that is equals to summation ei pi, and that is actually the definition of average energy. Average energy is obtained by multiplying the energy with this probability and summing it all over the possible states. This is actually the formula for average energy. So hence we have proved the first relation. There is a negative sign in here, which is a printing mistake in the book while writing down the problem statement, because if you see in the chapter where they had defined the average energy, you can find the negative sign in the formula. Okay, so it was a printing mistake right there, but you can see here that we have proved the first relation, and hence relation A is proved. Here we can see the first relation is proved, and now let's prove the second relation, which was the second derivative of this term, another derivative of this term with respect to beta, and proving it to be equals to something else. Let's recall here the second relation. Here is consider the second derivative of natural log of z with respect to beta and show that this is equals to this whole term, which is equals to this. Okay, so let's do that now. And as we have already calculated partial by partial beta of natural log of z, we'll apply another partial by partial beta on this term to calculate this term. Okay, so let's do that. To prove the second relation, I'll be using this. Let us call it as equation number 3. I'll use this one because we'll be applying partial by partial beta, so it should be in the form of beta. It shouldn't be in form of other variables. That's why I'll be using this one, because it's in totally in beta form. And let's write we need to prove. Let's write here what we need to prove so that we are clear about what steps we should be doing to reach to that form. So that is equals to ei squared e to the power minus beta ei by z minus brackets summation I e to the power minus beta ei by z whole square, and that is equals to summation I ei squared pi minus u bar square. Okay, this is the relation that we need to prove, and we'll prove it through this form. Okay, calculating this will become this at the end. So let's do that. My family members are always talking in the background. They can't keep quiet. So please bear with me. And we have from 3 partial by partial beta natural log of z to be equals to negative of summation I ei e to the power minus beta ei divided by summation I e to the power minus beta ei. Okay, that was 3. Now let's apply partial by partial beta, another one, on both sides of this equation. So partial by partial beta of this term, that is equals to negative just outside partial by partial beta on this term, whole term, that is summation I ei e to the power minus beta ei divided by ei minus beta ei. All right, let's simplify it. And for simplification, what I am planning to do is this negative is just outside. Okay, this side becomes partial square by partial beta square because it's double derivative. Okay, it becomes doubled, and negative partial by partial beta, we have two terms here. I'll use product rule here, okay, because it will be more easy. This is the numerator term, that is first term, and we have another term which is 1 over summation I e to the power minus beta ei, that's the second term. Okay, and we can write it as like that so that there is no fractional term involved. What I'm gonna do is, this is the taking it in the numerator and making its whole power negative, so we can use the power rule here simply. This is, let's say, the first term, this is the second term. Let's apply the product rule of differentiation, and this negative sign just remains outside. What we'll do is the first term as it is, this first term remains like that, ei e to the power minus beta ei, I'm using brackets, dot derivative of second term, this is the second term, e to the power minus beta ei whole power negative 1, then plus sign this second term as it is, dot derivative of first term, which is summation I e to the power minus beta ei. Okay, oh sorry, it's ei as well here, the same mistake I did before, and I'm filming it again because I forgot to write ei here. The first term has ei here inside the summation sign as well, another ei, so negative sign here, this term as it is, dot derivative of this term, and since it has a power on it, so we'll use the power rule of differentiation. And what does the power rule of differentiation is? So it's, if you have partial by partial x of x power n, then that would be equals to, this power comes here being multiplied, and x into n minus 1, power is reduced by one digit, dot derivative of inner term. Inner term is the term under the power, which is x. N, x to the power n minus 1, partial by partial x of inner term. So there are three things that will happen here. Power will come in the start. This power is -1, so it will come here, dot the whole term whose power it is, like this is the whole term, its power will be reduced by one factor. Whatever the power is, here the power was -1, so it will be reduced by -1 always reduced by -1, dot derivative of inner term. What is inner term? Inner term of power is this whole term, summation I e to the power minus beta ei. Okay, this is the derivative of power terms, and plus this term remains like that, so it's -1 power in the numerator, so it become positive power in the denominator, simply because its derivative is not involved. So we'll write it simply like that, and we'll take partial derivative of this term, summation I ei remains the same because it doesn't contain any beta, so the derivative will not be applied on ei but on this exponential term. And we know that what is the partial by partial beta of e to the power minus beta ei? It simply equals to e to the power minus beta ei dot the derivative of its power, which is minus beta ei, and e to the power minus beta ei derivative of its power negative ei will come outside, and partial beta by beta is remain inside. Partial beta by beta is 1, so we are left with minus ei into e to the power minus beta ei. So the derivative is minus ei into e to the power minus beta ei. Okay, that is something that we have done before as well. That is super easy, and we can write in next step this term to be equal to z in the denominator. That is something that we have defined at really first point, that this is equals to z, so we can write z in place of it because we want to get the needed form which contains some other terms. Let's simplify ei e to the power minus beta ei. I am writing them in brackets, and this negative sign remains like that. Then we have this term, it will become -1 becomes -2, so we can write -2 in place of it, and since it's negative power in numerator, it will become positive power in the denominator, whole power +2. Okay, dot derivative of this term, that's really easy as we have done it multiple times. So e to the power minus beta ei as it is, dot derivative of its power, which will give e to the power which will give minus ei. Then we have plus sign, and summation I, it will become minus ei square e to the power minus beta ei divided by z. This is z. Negative sign here. This negative and negative sign becomes positive. It's summation I ei e to the power minus beta ei bracket, and we can see here we have ei could be written first, and then e to the power minus beta ei divided by summation I e to the power minus beta ei whole square. This negative multiplies with this positive to become negative. Summation I ei square, and we can see e to the power minus beta ei by z, this is equals to pi. So we wrote instead of this pi, and negative summation I, we can see this is the same term and this is the same term. We can write them as whole square of this term because they are both same terms. When we have x dot x, when they are both same, we can write it as x square. Similarly, since both of them are same terms, we can write them as the whole square. I e to the power minus beta ei whole square minus ei square pi. Let's see what we wanted to prove at first place and compare that what else is needed to prove the form. Here is what we needed to prove, and we can see that ei square pi has positive sign, and yeah, that could be easily generated. Yeah, we have already almost, we are done. So multiplying negative sign inside, so it will become, this term will become negative and this become positive. We can write it first and then this minus ei e to the power minus beta ei whole square divided by e to the power minus beta ei whole square, and that is partial square by partial beta square natural log of z. As you can see, this term doesn't have any extra negative sign, but the first equation had a negative sign when we moved it onto the left side because it was there. Okay, it was always there, and we can see that we perfectly got what we needed here. Okay, it was ei square, this is pi, which was there as well. So they wrote z in the denominator here, this is z, we can do it as well. ei e to the power minus beta ei divided by, this is z, and since both of them are square, we can write them as one whole square. Okay, and that is what we need to prove. And from proof number one, you have seen, okay, let's get this form ei, and you can see e to the power minus beta ei by z, this is again pi, okay, whole square, and summation ei pi is average energy. We proved it in first relation, so we can plug it right into this equation. In place of this whole term, we can write average energy, that is u square, and that is what we needed to prove, hence proved. All of the relations are proved here. This was the first relation that we proved here, that summation ei pi is equals to average energy. Okay, and I simply wrote average energy in place of this. You can remove the brackets in the next step, and it's proved. All of the relations are proved. You can see here they were proved meanwhile getting to this form. Okay, so that was super easy, and this was pi and this was pi as well. And second relation is proved. Now let's prove the third relation. That is it, proved. Now let's see the third relation. The third thing is that prove that standard deviation in energy is given by this relation. This is the third thing that we need to calculate, that standard deviation in energy is given by delta u square equals to this double derivative. The result we got for the double derivative, because it's double derivative of beta square with respect to beta of natural log of z, which is equals to this. So we need to actually prove that delta u square is equals to this. Okay, that's, or this. That's really simple. Let's do that. We need to calculate the formula for the standard deviation in energy. Let me write it here. Delta u square equals, this is the relation that we need to prove, which is actually equals to ei square pi minus u bar square. For that purpose, we have to go back to the formula, to the general formula of standard deviation. What is the general formula of standard deviation? We'll put the values in it, and we'll see that it is equals to this double derivative value. Okay, so we know that The general formula for standard deviation in average energy is given by standard deviation in average energy that we secretly know is equals to, that average energy is equals to EIPI. Okay, this is our average energy. There is a summation sign here as well. Okay, U bar is equal to summation I EIPI. All right, we need to find out standard deviation in average energy is given by, so the standard deviation in average energy would be equals to, this is the general sign for the square of standard deviation because they required us to calculate the same. Delta U is for standard deviation and square of it means square of standard deviation, that is equals to summation of I. Then we will take EI, which is the energies. We'll take difference of it from the average energies, whole square, and probability being multiplied. This is the formula of standard deviation when we have probabilities involved. Okay, and if you want to know the general formula for it, then it is equals to delta x squared, that is equals to summation over I xi minus average amount, which is average energy here, whole squared multiplied by the probabilities. Okay, this is the general formula, and we have simply replaced the values with these values. Like instead of xi, we'll write ei, which are the instantaneous energies, and instead of mu, which is average, we wrote the average energy, which is u bar whole square, and instead of pi, we just wrote pi. Okay, so that is the average energy, standard deviation in average energy. Okay, so let's simplify it and get to the form that we need. So delta u squared, that would be equals to summation I. You should remember this formula, and if you remember this formula, you can adjust it to find out your required values for standard deviation for whatever variable that is involved. Okay, so summation I into ei minus u bar whole square pi, and let's open the square here. It's a whole term square, so ei square plus u bar square minus 2 ei u bar into pi. Okay, we just opened up the square here, and we now will multiply pi with all of these values. So it's pi ei square plus pi u bar square minus 2 pi ei u bar. Now next what I'm gonna do is to apply this summation on all of these terms. So it's summation I pi ei squared plus summation I pi only, because u bar square doesn't have I, so you don't need to write it here. Only ei summation I on pi will be applied, minus 2 summation pi ei only. U bar is written outside because it doesn't contain I, doesn't need to do anything. This term remains like that, pi ei square, because that is something we had in our proof as well. You can see here it's pi ei square, pi ei square. Okay, you just need u bar square, so for that purpose we are simplifying these two terms. Now here summation I pi, what does that mean? Summation I pi means summation of all probabilities, that should be equals to 1 by rule. Okay, total summation of probabilities is always equals to 1. There is no term being multiplied here, nothing else, only probabilities. All of the probabilities are being added because summation runs from minimum state to the maximum state, so that probability should be equals to 1. So instead of this, we'll write 1 here, so it's u bar square left, then minus 2 as it is. And this term, what this term is if you recall, then it is equals to the average energy, so you can put u bar instead of it, and this u bar is already there. So it's summation I pi ei square plus u bar square minus 2 u bar square. It's u bar into u bar means 2 u bar square, and it's plus u bar square and it's minus 2 u bar square. So what does that become ultimately? It's summation ei square pi plus u bar square minus 2 u bar square. You can take u bar square common, and what's inside is 1 minus 2 left, so you can easily solve it. 1 minus 2 is minus 1, so we are left with this term, and this is the standard deviation in average energy, that is equals to this, and which is equals to partial square by partial beta square of natural log of z, that we calculated here as well. You can see here that we got the same result for standard deviation as we got for the second derivative. So we have proved here that hence standard deviation in energy is equals to partial square by partial beta square of natural log of z. That is proved. I hope you got it, you understood it. And now let's calculate the next thing in series. The three of the formulas, three of the relations have been proved. Now let's do the fourth one. This problem is really lengthy. I have to split it in two parts, so I'll meet you in next part where I'll be solving and calculating the internal energy of harmonic oscillator and internal energy as well as the standard deviation for a two-level system. Okay, I'll meet you in next video.